Hello, friends, welcome. We shall continue our discussion. Last class, we understood that there are two approaches to control the speed of the synchronous motor by varying its frequency. The two methods, what we identified, are the true synchronous mode and self controlled mode. The true synchronous mode we discussed in the last class. Today we will look at the second method, self controlled mode. What is the self controlled mode? Here the rotor frequency is controlled as per the rotor speed. The stator frequency, what the AC supply we give to the stator, the frequency of that, it is controlled as per the rotor speed, whereas in the earlier method it was controlled by an independent oscillator. Okay, next, for this, when I mention the rotor speed with that as the reference, the stator frequency is controlled, then we need to monitor the rotor speed. Hence the rotor speed is sensed by means of suitable position or speed sensor. We require that speed sensor, and as a result of this, sensing the speed of the rotor and generating the frequency, giving it to the synchronous motor stator. Because of this, the rotor speed will always be synchronous speed. Rotor speed will always be synchronous speed corresponding to the control frequency, whatever frequency we are giving, corresponding to that, because both the speed which we are monitoring, according to that only we are generating the frequency. Hence the rotor speed and the frequency being hand in hand, the rotor will be running at synchronous speed. Are you catching that? Since we are monitoring the rotor speed, according to that only the frequency is generated and given to the stator speed. We have the rotor speed running at the synchronous speed corresponding to the frequency that we are applying. This method helps to avoid jittering or rattling, the hunting, the torque pulsations of the motor, and makes the running smoother without loss of synchronization. Without loss of synchronization. So, in the case of synchronous motor, that's a problem. The hunting is a problem. But here, since the rotor speed is monitored, according to that the frequency is controlled, both will be going on hand in hand. As a result, the jittering or rattling of the torque pulsations will be minimized, will be almost avoided. So now, having an idea about this method, we will look at the schematic. What is this method? How the realization is done? Look at the scheme. Observe carefully. Looking at the scheme, the working also will be clear to us. We have synchronous motor, we have controller, three-phase AC supply, rectifier, inverter, okay, synchronous motor. So we have the rectifier, a three-phase bridge, inverter, again a three-phase bridge, in between L and then C, the synchronous motor, the speed or position sensing, controller, producing firing pulses. Producing firing pulses. Are you able to see the schematic? The schematic. Okay. So now, with this schematic in mind, we will look at the working. The three-phase AC is converted into DC. This is the DC link. That is the DC link. So three-phase AC is converted to DC using this rectifier. Here the DC voltage what we get, it is smooth and stabilized with the help of L and then C. L and then C help to stabilize this voltage and smooth it so that the ripples are as minimum as possible. Almost constant DC being available here is fed to the inverter. So inverter consists of the controlled devices. Here we have shown the SCRs. It can as well be the transistors. The SCRs, the bridge converts the DC into AC with suitable firing pulses obtained by the controller. So what AC we get is the AC with variable voltage, variable frequency, ratio V by F remaining constant. You remember earlier we discussed about this. V by Fy, it is to be maintained constant to get the flux constant, thereby maintaining the torque constant. So the AC three-phase with V by F constant and frequency controlled is given to the synchronous motor. Accordingly, synchronous motor speed will change. Now, that speed is sensed by a position sensor or the speed sensor, and it is given to the controller so that the controller will give the output. What is the output of this controller? The firing pulses, 6 SCRs, 6 pulses. So it will judiciously decide how much is to be the value of alpha. Firing pulses, the value of alpha. And for that it uses a reference frequency. The reference frequency will tell me ultimately to what frequency I should come and keep the synchronous motor operating at that frequency continuously. Now, the controller will decide the firing pulses. Those firing pulses are given to the SCRs. Accordingly, the SCRs will operate, give me a voltage and then frequency of our requirement. For this, we use PWM. There are different PWM techniques, pulse width modulation techniques. Different PWM techniques are used. With the help of those PWM techniques, we change the voltage along with changing the frequency. Are you able to appreciate this? Now, with that input frequency, this speed can be gradually brought up to the reference frequency, making it to run at the expected speed. So look at the scheme once yourself and then try to appreciate what all is there in that scheme. Look at that scheme once and try to appreciate what all is there in that scheme. Yeah, look at that scheme. I will give a pause so that you will be able to appreciate the scheme yourself. Okay. Now we saw the working. That working, I will put it as three phase AC, two DC, two three-phase AC, two synchronous motor. Can we put it like this? So three-phase AC, what we are having here is fixed, whereas this is variable. So between three-phase AC, we have this DC, and this is called DC link. So such configurations are called DC link configurations. Okay. So now what we saw here, with change in frequency, voltage also will change. We make it change so that V by F remains constant, so as to maintain the torque constant. For variation of frequency beyond rated voltage, by chance we make the frequency change more. If I want to have more frequency, then the voltage also is to be more, but maximum voltage we can have is the rated voltage. If we make the frequency more than the one corresponding to the rated voltage, then the value of torque will decrease because V by F will decrease, and motor, the synchronous motor, enters into variable torque mode. The torque will not remain constant. This is to be kept in mind. Okay, now the V by F controlled and rotor frequency itself monitored will make the operation of the motor very stable. We get the stable operation of the motor. So that is the self-controlled mode. Why it is called self-controlled mode? It is called self-controlled mode because the motor speed itself is used for the control. Motor speed itself is used for the control. You compare that with the true synchronous mode, wherein we had the approach like this. The motor speed was not monitored. Instead, the frequency was generated using an independent oscillator. That's why, compared to this method, the self-controlled method is smoother. The pulsations of the torque will be less. However, there is this part coming into picture. This part, the speed is to be monitored. It is relatively more complicated. The speed or the position is to be monitored. Now you can make a comparison between the two, the true synchronous mode and the self-controlled mode. The comparison between true synchronous mode and the self-controlled mode, that is relatively simple. This is complicated, whereas the advantage of this is, here the rattling or the pulsations will be relatively less. Okay. Now, with an idea about the control of the drives, we will look at the applications of the synchronous motor drive. The synchronous motor drive applications. Normally, the synchronous motor is employed for very large capacity applications. Please keep this in mind. Very normal application of synchronous motor is wherein the capacity required is huge and the speed involved is low. high capacity low speed, high capacity low speed, and speed normally remains constant. Speed normally remains constant. For such applications, the synchronous motor drive is employed. And synchronous motor is also employed as capacitor. This we have already seen. The field current changed, giving us leading PF, making it to act like a capacitor. Then it is called a synchronous condenser. We discussed now. We can use it as a synchronous condenser also. It is used for PF improvement. It is used for PF improvement. So we will look at the application specifically when we take up the applications. We will make a reference to this again there. Okay, look at this. What I expect you to keep in mind is the large capacity, low speed, speed almost constant. These are the three aspects to be kept in mind when we think of synchronous motor. Is it okay? Good. So with that, we are coming to the end of synchronous motor drive. We will stop here. Bye. Take care.